All right, so now we have video 2 of week 2. We'll be talking about Skew-Ts and upper air data. So going up from the surface where we were last time, meteorologists use radiosondes to measure the state of the atmosphere aloft. These are typically what you see when you see weather balloons. Weather balloons are really the balloon that's lifting it up. Radiosondes are the instrument package that balloon's taking up. Now these radiosondes, the standard ones that are used in the US and around the globe, they contain pressure, temperature, and humidity sensors, as well as an altimeter and or GPS system to track position and height. They don't contain sensors in and of themselves to measure wind, even though wind is a very critical quantity that we are trying to observe through these upper air systems. Wind instead is derived from the drift of the balloon because these balloons are known to have a certain buoyancy at the surface, and making some reasonable assumptions about the temperature of the gas inside the balloon as it goes up, we can derive essentially its buoyancy, its ascent rate, and compare that to its position tracking over time to rederive what wind it was experiencing as the balloon followed the flow. And again, I sort of mentioned these are launched all around the world. There's around 900 locations around the globe where these are regularly launched. Typically twice daily at 0 UTC and 12 UTC. Now remember, UTC is the time along the central time zone where there's no offset. In Ames, Iowa, we're in the central time zone right now. We're in central daylight time, so that means that we are -5 hours from UTC. So say the Davenport office, National Weather Service office, over on the eastern side of the state is where our nearest radiosonde launches are, or maybe Omaha, depending on where you're at, specifically in central Iowa. But both are in the central time zone. So right now during the summer and most of spring and fall, where we're on daylight savings time, these are at 7 p.m. and 7 a.m. During the winter months of the year when we're on standard time, we're instead, central time is a -6 offset from UTC. So these launches happen at 6 a.m. and 6 p.m. Though, that being said, special launches of these do occur as needed, especially when more frequent sampling is needed for a particular weather hazard that's coming up. Still, even though we have somewhat, you can think maybe from this map, we have good coverage over maybe the continental US, Europe, and Eastern Asia, it's still generally sparse compared to, well, of course, what do we want? We always want more data to incorporate into our weather forecast, but you can see it's especially sparse over the ocean. It's hard to regularly launch balloons where there's no land sites to have a station to launch them from, as well as much of the tropics and the southern hemisphere. One, again, oceans, but two, even where there's continents, there's less of these stations regularly launching balloons. So there is a problem trying to regularly sample the upper parts of the atmosphere with these radiosondes. There are other techniques to help fill in the gaps. One of the big ones is remote sensing that we'll talk about in the next video. But just so you know, we launch these about usually twice daily around the globe as a meteorological community, but they still don't cover nearly enough what we'd want to have for upper air data. So taking a look at what the kind of things we get out of this is of course the post-process data. We can get things like our pressure as we go up. We get our heights, our temperatures, dew points, and then you can express your wind either as your horizontal components or as a direction and speed. And then this is just our constant metadata about this particular location. This is the Lincoln, Illinois station where this was launched from. And this is an 18 UTC special launch. And if you recognize this date, that was when the derecho that came through Iowa and into Illinois. This was a special observation to help sample the environment ahead of that derecho as it was heading towards Illinois. So this, as an 18 UTC, would have been a 1 p.m. observation on August 10th there. And just a quick little note, not all required, but if you're interested in Python programming, I am. The examples that are going to be following are all Python plots. And you can figure out how to do these kind of Skew-T diagrams and plot real radiosonde observations following this example right here, this link. So, an initial attempt to sort of plot these data, if I just sort of, knowing that, of course, pressure decreases as you go up. So I'm going to start with low pressure, go to high pressure, and just straight up plot temperature and dew point. You get something that looks like this. Now there's a slight problem we've talked about in our first week's video content, that pressure decreases exponentially with height. So it doesn't really make sense to have a linear scale for pressure. So let's adjust it a little bit and use a log scale for pressure. At least now we're sort of a little bit more physical of a distance from the ground, more similar to height of what we'd expect to see. So we have a log pressure scale. However, it may not be entirely obvious here, but little important differences in temperature are kind of hard to see because of the general tendency, as we also talked earlier in this class, for temperature to decrease with height in the troposphere. We want to accentuate and see these differences a little clearly, especially when we say want to plot multiple profiles. For instance, this is a parcel of air that starts at the surface, and if we assume it doesn't have any heating or cooling exchanging with the environment, it just goes up from the surface, what it would take. That's what this little parcel of air that starts at the surface, and if we either forced it or let it rise up, depending on if it's buoyant, positively or negatively buoyant. Those details we'll get to with severe thunderstorms later in the course when we talk about stability. But if we're plotting multiple temperature profiles on this, it's kind of hard to see the important differences where they're close together because, again, there's always this general pattern of decreasing as we go up. So we do a little trick. We skew the x-axis, our temperature axis over here, to get a Skew-T, so we get skewed temperature axis, log P, because we have a log pressure scale. So that's the name of this general chart, a Skew-T log P chart. Since we use these all the time in meteorology, we are kind of lazy, we just say Skew-Ts. But this is generally what they are. They have temperature, so if it's 0 degrees, it's anywhere along this line, or an isotherm line of constant temperature. So our lines for our x-axis are slanted. This is at a 45 degree, depending on the exact source, the angle varies slightly, but they're always skewed like this. So this is 0, this is -10, and again, you see it's going back by 10 degrees Celsius on each of these lines. So even these skewed ones, it keeps on going. So for instance, this one's -30, this one's -40, -50, so on and so forth. So as you can see, we can accentuate our differences between these profiles a little bit more clearly. We can see up towards the top, where we're getting to the top of the troposphere, getting towards the tropopause, where we reach the stratosphere boundary. We can also see this clear change in direction, versus in our previous one, it was a little bit harder to tell if that was just a little change in the pattern or if it was something important. So this is the general method of what a Skew-T is. And it's a really useful way for plotting these upper air observations that we take from radiosondes. Of course, right now I just have temperature and dew point on here. So we're just going to do a quick little sample of reading this. So say at 500 hectopascals, or 500 millibars, we can look at our constant pressure line, our isobar, going across, and then we can sort of read our data going there. So right here, our dew point line is pretty close to this isotherm, so we follow the slant down. It's about just less than negative 30 degrees Celsius. If we instead are at our temperature, you see it's slightly above this isotherm, so we take the slanted line, go down, so it's just above negative 10 degrees Celsius. And if we look at our partial temperature, it's over here. It's, it's closer to this isotherm than this one, but let's look at what those are. So it's 0 to 10. So it's probably somewhere around 3 degrees Celsius if we had to guess between these lines. So we also have wind data. So if we want to plot wind along with this, we can plot our nice wind barbs along the side, sort of standard convention where west wind is off to this side, east winds, the barbs are sort of off this way, southerly winds would be turned down, northerly winds turned up. So you can see how the wind speed changes by the number of these little short and long barbs and sometimes flags that show up, and the direction changes with height as well, which both will become very important once we get to the severe thunderstorm unit later in the course. And this is a full-out thermodynamic diagram. If you're a chemist or a chemical engineer, you're used to all kinds of different thermodynamic diagrams. This is probably the severe weather meteorologist's favorite thermodynamic diagram. We use these all the time. So there's lots of supplemental lines that you can often see on these when you go looking for a Skew-T that you aren't plotting yourself. And some of these we'll talk about in more detail once we get to the severe thunderstorm unit. But otherwise, know that you can ignore them in the background for just basic interpretation of the data. The key thing to find are your skew lines for temperature, so that you can always reference back to what your temperatures are, as well as the horizontal lines for your pressure levels. And then not losing sight of the main lines that are plotted on top for your actual profiles. And just sort of as a heads up, sometimes if you go looking for these plots, they come with lots of extra good data. Of course, it may not be good if you're not trying to find it. It may be confusing. So just to be a heads up, this is what the official SPC produced sounding plots look like. They have your standard Skew-T here, some supplemental vertical plots, something called a hodograph. We may or may not get to that once we talk about severe thunderstorms. And then a whole bunch of parameters and interesting things about different severe likelihoods and all sorts of stuff like that. Again, things that we do not at all have to worry about now, and we'll only maybe worry about a little bit once we get to the severe thunderstorm section of the course. So again, what's important right now? Knowing that this is a skewed temperature axis, so knowing how to read what your temperatures are at any isobaric level. Know that your winds are plotted over here on this side, and that you have a log pressure scale as you go up, so it's a little bit more representative of what the actual depth of the atmosphere looks like. So those are all fine and good if you want to look at a single station's data. But what if instead of looking at all the levels for a single station, we want to look at all the stations for a single level? So that's where these upper air plots come in. Now, if you noticed from the very beginning, there's a lot of weird decimal points in all those pressure levels. So how do we know that as it's sampling, the radiosondes going up, that we're going to get consistent levels out of all of these different vertical profiles, say, across the US? And we only can do that without interpolation or weird business because there's something called mandatory levels, that these instruments are always going to report values at these particular required levels. You can look at this link from the AMS glossary to sort of see a little more description of what these are, but I have a summary of the ones that are most relevant here. So sort of our lower troposphere levels, 1000, which is usually pretty close or even under the surface. So you can't include the data if it's below your surface pressure, your actual station pressure. 925 and 850 hectopascals or millibars. Again, those are equivalent units. Middle of the atmosphere, you have 700, 500, and 400. And then upper, this is where you look for things like jet streams, 300, 250, and 200. Now, we'll talk more in next week's about large-scale weather systems, about where and what you can find at each of these levels and what and why they matter. And there's a bunch of additional upper levels, mandatory levels that are at 150 hectopascals and above. If you're interested in those, check that. You won't be required to worry about that for anything for the purposes of this course. So, just sort of as an example or a starting point, 500 millibars is probably the most common of these upper air plots that you're going to see. The reason why is because, again, pressure is the weight of the air above you. Typical surface values are about 1,000, so that means 500 is about halfway by weight of the column of air above you in the atmosphere. So it gives a nice middle waypoint to assess things. And it's far enough away from the surface that you don't really have to worry about frictional effects, which makes a lot of the analysis a lot nicer. So if you just were to plot the observations, you get these kind of things that look like modified station models. The wind barbs are constructed exactly the same way. Instead of pressure, because these are all at a constant pressure, they're all at 500 millibars, we instead plot the height of the observation in the upper right-hand corner. And then we also have temperature. Little weird thing, it's in degrees Celsius, and then we sometimes the dew point, instead of actually being dew point, it's, notice these are all positive values compared to you can't have dew points higher than your temperatures. These are actually dew point depressions. Again, details you don't have to worry about, but they may look funny if you're trying to interpret it. The big conclusion about upper air plots is, unless you're actually trying to do the meteorological analysis and do all this by hand, it's a lot nicer to get plots that look like this, where the fields are already analyzed, where there's contours already drawn out either by an expert forecaster using their knowledge of the weather systems to interpolate things out in a physically realistic way, or, as we'll touch on a little bit in the next video, there are computational models that can gather in all of these data and assemble sort of what the continuous fields look like in a physically reasonable way. And so that's an example of what this is. So you can fill in these lines of constant height. So where height decreases on a constant pressure surface, that's the equivalent to a low pressure system because your pressure is closer to the ground, which means you're at a given level, your pressure has to be lower. So you can see all these sort of wave patterns. We'll be talking more about that later. And again, you can see humidity lined up here in these different lines for temperature values as well. Again, a lot of these kind of things, even though we can get a little close up if you're interested in seeing the details of what this looks like, sort of like here over in Davenport, you have a 50 knot wind. And the direction is kind of similar to following the wave pattern of these height lines, which is something, again, we'll talk about later. A lot of these kind of things are just to get you the exposure to know that these plots exist and the basics of what data are shown on them. And we'll be talking a lot about more of what these meteorologically mean later on. So with that in mind, again, I got kind of ahead of myself. My first item is that there's a lot of these details that are missing, like what a Skew-T means for severe weather, all those different things I was talking about, those parameters shown, and all the details of what the wind changing with height, all that means. And, for instance, what all those patterns you might have seen in the upper air plots. Those will be addressed in future weeks as we sort of build up our meteorological knowledge. Right now, the main thing is to get exposure and know that these are the kind of plots that exist and the data that we can see on them. Other reminder, discussion post and quiz for this week are both now available. Be sure to check those out on Canvas. If you have any particular difficulties with the figures, of course this is a week on measurements and maps, so there'll be maps in the quiz. If you have difficulty viewing any of those, please let me know right away. I'll be sure to work with you to get something worked out so that you can properly and fairly take the quiz. And the next video coming up, we're going to be talking about weather models, something that I'm particularly interested in. So hopefully that'll be a fun video coming up. Thank you, and I'll see you then.